Okay, hello everyone, and welcome to the presentation of this paper. The title is Frequency Support of Fast Multi-Energy Storage System in Low Rotational Inertia Scenarios. The authors of these papers are Anne Meyersdal from the Arctic University of Norway, Marta Noemi Acosta from the University of Nuevo León and also University of Southeastern Norway, Professor Jose Luis Rueda from Delft University of Technology, and finally Professor Peter Palensky from Delft University of Technology. I am Professor Francisco Gonzalez and I will be presenting this paper. Um, Let's start with a short introduction. As you must be aware, power systems are changing dramatically and quite fast in recent time, especially because the introduction of many technologies using power electronic converters, especially for power system application. One of the consequences of this integration of power electronic converter technology is the let's say the reduction in the number of synchronous generators connected to the grid, and as consequence the total rotational inertia of the power system is reducing and is already creating problems in many power systems around the world, and there are concerns in others. Basically, the reduction of the total rotational inertia is making the transition faster and deeper, especially for frequency. And that is the reason that we decide to write this paper where we are including the concept of fast multi-energy storage system. Fast because we are using technologies that they have extremely fast response. And here, what we are doing is two main contributions. The first contribution is providing a full detailed model about the fast multi-energy storage system, especially including two technologies, supercapacitors and flywheel. And those devices they are equipped with controllers, frequency controllers, and the frequency controller is basically a combination of proportional and proportional derivative. And the second contribution here is that we are assessing the frequency indicators in a multi-area power system considering decreased inertia scenarios. I must be clear from the very beginning. The type of modeling that we are using here is creating model for system frequency response, because that is the research area that we are doing now. Okay. The first thing that you must imagine is that we are using a three-area system. A classical area has a synchronous generator, of course, a load, and one multi-energy system. In this case, the multi-energy system, of course, is equipped with sensible frequency controllers, okay? The three main elements that we need to take care from the modeling point of view is first the synchronous generator, and we need to fully define the model for the turbine generator and also the rotating mass and the load. Second model that we need to take care here is the one related with the fast multi-energy storage system. And finally, because this is an interconnected three-area system, we need to take care about the modeling of the intertie connecting. And well, the modeling is very well defined in the case of the rotating mass and the load. They are a first order differential equation that is very well known, that is including the effect of the power imbalance and also including the effects of coming from the loads. Here we have the first order differential equation, the set of two first order differential equations describing the case of the reheat steam generator that is used in each one of those areas. Okay. Finally, we have here the model, and this is a first order differential equation combined with some algebraic equations. And the idea here is that we can define in a proper way the dynamic of the power flow moving through those transmission lines. Next stage is the second component, and that is the multi-energy system. In this case, the multi-energy system have two main components. One is the flywheel, and the other one is the supercapacitor. In this case, we are starting with the electromechanical dynamic of the flywheel that is represented by three first-order differential equation, where the model include the time constants related, for instance, with the rotational inertia of the flywheel, but also time constant related with the frequency settings. Okay. In this case, we are including that when the flywheel is releasing energy, of course, the rotational speed is changing, and we are including the definition of state of charge for this supercapacitor in order to take care about changes on rotational speed. In this case, we have included the frequency controller. As you can see over here, there is a proportional action and also a frequency sensitive component that is included here inside the other. In this case, right now, we are presenting the model of the supercapacitor. For the supercapacitor, we are considering a model that go up to the internal storage charge inside the supercapacitor. And also there are equations, algebraic equation, very complicated algebraic equation to represent the physical behavior of the internal voltage. Of course, we are including also the state of charge variable because, again, we are interested in keep control about what the state of charge is. And here we have again the equations defining the frequency control. Here we have the proportional controller, as you can see. Okay. Finally, what we have done is something very simple. What we have done is creating the differential algebraic model that we have presented before for the power system that is represented by three areas. And the model have been implemented using MATLAB, in this case, the release 2019B. All the equations were implemented inside, and we are using a solver, a time domain solver for the differential equation, the ODE 15. Okay. Then what we are doing is considering the frequency response. We are considering two main scenarios: the system without any kind of additional frequency support from the multi-energy system, and then we have another case that we enable the multi-energy system to provide frequency support to the power system. The disturbance here, the frequency disturbance, is basically a step low change. We are talking about that we are including one in area 1 and one in area 3. Both of them happen at the same time, 1 second, and both of them have the same amplitude. And then we are collecting the time series of different variables. One of them is the frequency deviation, and we are interested on several indicators. In this case, the maximum frequency deviation, the minimum frequency, and of course, the minimum time. Then we propose three simulation scenarios. The first scenario is considering the original inertia in this system. Then we decrease the inertia 25% in each area. And finally, scenario 3, we decrease the total inertia 50%. Here you can see that in this case, scenario 1, there is not any reduction on the inertia, and we have case 1 and case 2, and we have independent indicator for area 1, area 2, and area 3. What is important to see over here, what is interesting to see here is As you can see, from the minimum frequency, of course, having the multi-energy controllers activated, they provide a better minimum frequency. And that is because, of course, as you can see, during the under frequency event, the supercapacitors and the flywheels, they tend to contribute to the power imbalance. Scenario number two is similar to scenario number one. We have two cases, one case without a frequency support from, and one including the multi-energy system and providing frequency support. And in those cases, again, we are reducing the inertia 25%. And as you can see over here, there is a massive improvement when you include those multi-energy systems. Scenario number three, we include again the multi-energy system, and right now we are reducing the inertia to 50% of its original value. And again, the multi-energy system has demonstrated the ability to provide power during the disturbance, and as consequence, it was able to improve the frequency response. Well, conclusion of this paper. The first conclusion is that we deliver a full differential algebraic model that can be used by someone else. This model include the system model, the power system model, but also include the model for multi-energy system. Specifically, we are including the model of one supercapacitor and one flywheel for each area. And then we performed the simulations, including the flywheel and reducing the total system inertia. What is important to conclude here is that low inertia values, low rotational inertia, produce faster and deeper changes in the frequency. And that is the case number one in the three different scenarios. However, when we include the fast multi-energy storage system, that is the case two, we improve the frequency response. We are able to reduce the minimum frequency and the maximum frequency deviation, and that demonstrate we know that including a multi-energy system that is extremely fast help to control the frequency. Well, that's all for this paper. Thank you very much for watching. I hope you enjoy. Thank you. Time for question and answers.